Hey guys, it's Professor Sweeting, and this is the second online lecture of the semester. In this video, we're going to be discussing the NorthWest corner method, which is the first algorithm that we'll look at for solving the transportation problem. Regarding or using the tableau for that problem. All right, so like many of the other management problems we've covered, the transportation problem, which is easy to state, is not necessarily easy to solve. That is to say, there's no algorithm that is guaranteed to give you an optimal solution in every situation. However, like in the problem of bin packing, there are a number of well-known algorithms that each produce solutions with some particular favorable property. So the first that we're going to look at is called the NorthWest corner method, right, for the transportation problem. So I'd liken this to the next fit algorithm in that its virtue lies in its speed and simplicity. So this algorithm is nothing more than a way to devise a shipping policy that fulfills the required demand. So recall that a shipping policy is an assignment of the number of units that each distribution center is to send to each store, right? So, or each source location, if you will, is to send to each destination location. All right, and it's an assignment such that the total number of items that distribution center 1 sends out, or that each distribution center sends out, doesn't exceed their total supply, and the total number of product that each destination location receives meets its demand. Okay, so here are the steps of the algorithm. So the first step is to locate the upper left cell of the tableau. Right, so in this case, it's this cell. Right, so there'll be two rim conditions for this cell. So one for the row, right, so that would be this rim condition, and one for the column, that's this rim condition. We take the smaller of those two numbers, say S, so in this case, S is 40, to be the new value of the cell. So that's what would go here. And I guess I should do it here. So I created another tableau on another page for carrying out the algorithm. But I guess I'll just do it here and maybe do it again. We'll see. All right, so we identify the two rim conditions for the upper leftmost cell, right? We pick the smaller of the two and we take that to be the value of the cell. Okay? If there's a tie, we choose the rim condition corresponding to the row, right? Or we select the row. I don't know. You'll see why that's necessary in step 2. So in step 2, we cross out the row or column that had the rim value S and reduce the other rim value for this cell by S. So here, what we do is we cross out the row. Since we took the rim condition from the row, we cross out the row of that cell, and we subtract its other rim condition, which is the column rim condition, by that value. So this now becomes 30. Okay, I guess it is necessary to continue on the next tableau, the other tableau, but this just illustrates the first two steps, right? Okay, so the third step, or maybe not. Okay, so the third step here is to repeat steps 1 and 2 for the remaining not crossed out cells until a single cell remains. All right, so let's do that. So we end up with kind of, just imagine deleting this row entirely from the table. All right, so imagine that this row is on here. Then you kind of have another tableau, right, that you can then repeat steps 1 and 2 for. Okay, so nothing about this algorithm assumes that we're dealing with a square, okay? All right, so it's perfectly valid to consider this as a new tableau. All right, so like I said, most of the problems that we'll look at will have an equal number of source and destination locations, but that's not necessarily the case. All right, just makes the diagrams look nicer. Okay, so in this new tableau, we repeat steps 1 and 2. So we locate the upper left cell. So there are two rim conditions. There's the one corresponding to the row, which is 50. There's one corresponding to the column, which is 30. We take the smaller of these two numbers, right? In this case, it's 30. And we take that to be the new value of this cell. So if there's a tie, we choose the rim condition. Okay, all right. So there's no tie. Okay, so we take 30 to be the new value of this cell. Okay, and what we do is we then cross out the row or column that had the rim value right? So we cross out the column, we took the column, the rim condition of the column for this cell, and then we subtract the other rim condition by this value. So this now becomes 20. Okay, and so now we have kind of like, here I have 2 pencils. We have a new tableau, which is these 2 cells and these 2 cells. These rows, these columns. And then these central cells. So you can just kind of disregard the row and column that we've crossed out. And then we repeat steps 1 and 2 for this. Alright, so we keep doing this until we're left with 1 cell. Alright, so, okay, we look, this is the upper leftmost cell of the tableau. And we look at its rim conditions. We have 30 for the column it's in and 20 for the row. We take the smaller of the 2 to be the value. Okay, and then that was the row rim condition, so we cross out the row and subtract the other rim condition by that value, so that now becomes 10. Okay, and then we end up with a new tableau, which looks like this. It's this 1 row and these 2 columns. Okay, and then just these empty cells. Alright. This is the upper leftmost cell of this new tableau, and it has rim conditions 10 and 60. We take the smaller of the 2 to be the value for that cell, and we cross out the column since that was the rim condition corresponding to the column that cell is in. Right? And then we subtract that value from the other rim condition. And then we're left with a tableau that just has, I'm using all my pencils here, we're left with a tableau that just has 1 row, 1 column, 1 cell. So that is here, alright? So we repeated steps 1 and 2 for the remaining not crossed out cells until a single cell remains. Here's our single cell. There's a tie for the rim conditions of both the row and column, and that's because of our assumption that the total demand is equal to the total supply. So we just take this value to be that, or we take the value of the last cell to be this value, and then the procedure ends. Alright, so there you go. Okay. Alright, so this was just a restatement of the problem and a new tableau that was to be used for that example. But, alright, let's fill in this new tableau with the information of the previous one, now that we've applied the northwest corner method. And we'll see if the values of the cells that we have here correspond to a shipping policy. Alright, so 2, and then we'll also compute the total cost of that shipping policy. 4, 3, 2, 2, 3, 3, 40, 30, 20, 10, 50, 70, 30, 50, 40, 20, 50, oh, that's 60. Oh, kind of goofed here too. So we're filling in the ordinary or the regular tableau just with this information. So we're disregarding all of the changes that we made to the rim conditions. The rim conditions just help us keep track of the supply that's provided by this distribution center of this column, and also the demand of the store of that row, of every row. Okay, so 150. Okay, so this is the tableau we get when we apply the northwest corner method to that transportation problem. So to the tableau that contains all of the information of that transportation problem, which is restated here. Okay, let's see if this gives us a shipping policy. Well, we see that the sum, so you can take in, empty cells to have a value of 0. So what this says is that distribution center 1 sends 40 MacBooks to store 1, right? And distribution centers 2 and 3 send 0. So the total number of MacBooks sent to store 1 is 40. Okay, that's good. So the demand was met for that store, right? Here we have that 30 MacBook Airs are sent from distribution center 1 to store 2, and 20 are sent from distribution center 2 to store 2, right? For a total of 50 MacBooks sent to store 2, right? So that equals the demand, so we met the demand of store 2. And lastly, for store 3, 10 MacBooks were sent from distribution center 2 to store 3, and 50 were sent from distribution center 3 to store 3, right? For a total of 60 MacBooks sent to store 3. So its demand was met. So we met the demand. Let's see if we didn't exceed the supply that each distribution center can provide. So distribution center 1 sent 40 MacBooks to store 1, 30 MacBooks to store 2, for a total of 70 MacBooks. So we did not exceed the total number of MacBooks it has. Distribution center 2 sent 20 to store 2 and 10 MacBooks to store 3, for a total of 30. So we didn't exceed the supply. And lastly, distribution center 3 sent all of its MacBooks to store 3, for a total of 50, and we didn't exceed its total supply. All right, so what we end up with here, this filling in of the tableau, is a valid shipping policy. Okay, so what is the cost of the shipping policy? Cost. Well, we multiply the number of MacBooks sent from that distribution center to this store by the cost per MacBook to ship. So it's 80 plus 120 plus 60 plus 30 plus 150. Okay, so this is 90 plus 80, so 270 plus 170, which is 440. Correct me if I'm wrong here. So 290, yeah, okay, so 440. So it's a total of $440 for this shipping policy to send these MacBooks from these distribution centers, these particular distribution centers, to these stores in these quantities. Okay, so as you can see, this method completely disregards all shipping costs. As such, we can't expect any shipping policy produced by the NorthWest corner method to be optimal. We completely disregarded the values of these cells. All right, so in the next lecture, we'll look at two other algorithms using tableaus, the least cost method and Vogel's approximation method, both of which incorporate shipping costs into their solution, right? So the shipping policy that these two algorithms produce will look at and will consider the shipping cost associated with each distribution center and each store. All right, so that's going to be important as far as obtaining a somewhat reasonable shipping policy. All right, so for example, we might have wanted to send all of distribution center 3's MacBooks to store 1 because that's the cheapest cost that we have possible, right? But see, the virtue in the NorthWest corner method is just that it's a simple and cheap algorithm just to get a shipping policy up front, okay? All right, so later we'll also discuss an algorithm called the stepping stone method, which doesn't necessarily give us a shipping policy directly, but rather is used to improve any existing shipping policy. So including the one found by the NorthWest corner method and the others as well. So, once you have this information in the tableau, right, you have a shipping policy, this stepping stone method is used to make amendments to this shipping policy in a uniform way that should improve on the shipping cost. I just also want to note that, we made a number of assumptions about the problem that have greatly reduced the complexity. Namely, we're looking at only one product being distributed from these distribution centers to these stores. We're also considering that every distribution center can ship to each store, which may not be true as well. And then there may be certain constraints, some linear constraints, just as we had in the case of the linear programming problem, where distribution center 3 has to send at least so many of the unit to store 1, and so, or for distribution center 3 for some reason can't send more than twice of its units to store 2 as it does to store 1, something like that. And so in these complicated problems, these do have applications in real life. In these problems, they extend this tableau to include that information, and you can do further analysis and other algorithms with that extended diagram, with that extended model. All right, so that's the end of this video.